Hello. Yeah, I am audible. Please write in chat box. Okay. Yeah. So deflection of wings. Up till now, we considered uh, what is the stresses. What is the stresses that originates in the beam, that is can be bending as and shearing, uh, shear stress. Now, because of this bending stress, what is the deflection that originates in the beam? Okay, because as we know, if we apply simple normal stress, then we can just reduce from this equation what is the strain originates in a body. But when bending stress is there, what is the deflection that occurs in the beam? Beam can be simply supported cantilever, load can be point load, uniformly distributed load, uniformly varying load, anything. So what is deflection of what value of deflection? And in deflection also we obtain slope. So both things, what is the slope and deflection? So to solve this, there are three methods. First is double integration method, double integration method. Second is Macaulay's method, what you say. And third is moment area method, moment area method. Now, if you look at these three things, so in double integration method, when a body is in means when the uniform, load is uniform, you can use this. Okay, but and in Macaulay's method, load can be uniform or point load with uniform load, you can use this. And in moment area method, these are generally useful where geometry of the body or beam is not uniform. Geometry of the body or beam is not uniform. Suppose, if we say, suppose it is given that this is the beam and this is a support. So you apply one load, you can easily solve with double integration method. Okay, you can also solve with Macaulay's method, and you can also solve with moment area method. Now, if we just make it little complex, you have this support. You apply one load, one uniformly distributed load, then another load. Okay, so if then the useful method is this Macaulay's method. But if suppose the beam has given the cross section and it is changing, suppose this is the cross section of the beam. Okay, now what will you do? How will you solve the problem? Then the moment area method will be applicable. So uh, um, uh, there are few things that you need to remember. Double integration method is good for simple problems, and for other problems it is tedious. Then Macaulay's method is good for problems with uniform beams and for any types of load. And moment of area method is good for even these problems also you can solve with moment area method and this also. But you need to know the area, because here the area concept came. So you need to know the area of any shape. So I am going with it. So first double integration method. So suppose uh, the few things you need to remember is that elastic elastic property into moment of inertia and double derivative of y is equal to moment acting, that is the moment acting on the beam, acting on the beam. Okay, that is how we pronounce it, like ei d2y by dx square is equal to 1. Suppose this is your beam. Okay, your beam has elastic constant E, moment of inertia I, given moment m. Then the shape of the beam would be like this. Suppose if I apply load here, the shape of the beam would be like this. So this deflection, the y deflection is given in here, and the distance x with respect to x is given here. So now a few general things. So if I integrate it once, ei dy by dx is equal to m integral dx. So this is called the slope. Okay, if I integrate this, this is called the slope. And if I ei y is equal to double integral m, this is called deflection. Okay, now if I write it like ei d3y by dx3, this is called shear force. Now why shear force? Shear force is equal to dm by dx. Okay, now if I write it like ei d4y by dx4, it is called rate of loading. Rate of loading. That is useful in uniformly distributed load. That is small w. Okay, it is negative. So please remember this. So now I am going to consider a problem. Suppose you have a beam. Okay, suppose you have a cantilever beam and your P load is acting here. Given the elastic properties are E and I, so you need to find the deflection. Suppose this is A, this is B. You need to find the deflection at point B. Now applying the double integration method, we know that ei d2y by dx2 is equal to m. Okay. Now suppose take any section x, and what is the moment? Minus p into x, because the load is acting. That will tend. There is a sign convention. I'm going to show you how that is coming. So this minus sign is coming because of the clockwise. Means whenever is a hogging condition, you need to take it minus. Okay. Whenever there is a hogging condition, and when there is a second condition, please take it plus. So this P load is trying to means bend it like in downward direction, and it is acting clockwise. So take it minus px, and as you also can see that anti-clockwise moment is taken as positive. Now if I write in this way, integrate it once, ei d2y uh, uh, by suppose I integrate it once, what will it become? Ey I dy by dx is equal to minus px square by 2 plus c1, one constant. Okay. Now second integration, ei d2 by sorry ei y is equal to minus p x cube by 6 plus c1x plus c2. So this is the basic integration. Now we need to obtain the c1 and c2. So what will be c1 and c2? When for the cantilever, both the properties occurs at point A, that is uh, at x is equal to L. Okay, because we are taking x from here. So at x is equal to L, dy by dx is equal to 0, and y is equal to 0. What the meaning of this? This means slope is equal to 0 and deflection is equal to 0. That means this body will don't have any slope at this point and at this point, and also don't have any deflection. Now to put that, at x is equal to L, y prime, that is dy by dx is equal to 0, and y is equal to 0. So if we put at x is equal to L, okay, and this is 0, so then c1 would be e L square by 2, and if put here at x equal to L, it comes uh, if we write the C2, C, just kill. Okay. Now, what is the C2? 0 is equal to minus P L cube by 6 plus P L cube by 2 plus C2. Now if we transpose it there, then C2 is equal to minus W, if we write 6, 4 minus 1, W, sorry, PL cube by 3. If you solve it, okay, that means we got the two equations. Now we can write it as uh, y is equal to minus P x cube by 6 plus P L square by 2 into x plus, sorry, minus P L cube by 3. Now what is the maximum deflection? What is the location where maximum deflection would occur? And sorry, here also EIY. What is the, so at x is equal to 0, you can see from the general intuition that at x equal to 0, maximum deflection would occur. That is y. So at y is equal to 0, sorry, x equal to 0, y is equal to PL cube by 3, and that is negative. Negative is coming because deflection is in negative y direction. And what is the slope? Slope is equal to dy by dx, that is equal to, if we put x is equal to 0, then it will be, sorry, EI. Dy by dx is equal to, if we put where the equation of the slope is here. So if you put x equal to 0, then constant C1 will remain and it will be PL square by 2 EI. So for cantilever, what we got is from the double integration method. For cantilever, for cantilever, y maximum is equal to PL cube by 3 EI in negative y, and theta maximum, that is slope, is equal to P square by 2 EI. So this is condition for cantilever at point load. Uh, any problem up to this? Is it okay? Hello. Now I'm going with the next part. So please, if any question, please stop me in between. Or now the second question is, suppose the same cantilever, sorry, the same cantilever, if I am applying a load at some other point. Suppose I am applying at the end point. Now I am applying the load at this point and I want to, suppose this is A, B and C. I have to take solve y at C and theta at C. What is the value of this? So can anyone guess how we solve it? Any of any method you know? So I'm going to tell you just a couple of minutes. So suppose if it is given at this point, you know the point, the formula is, if it is given at this point, you know formula delta is equal to, sorry, y is equal to PL cube by 3 EI, this is P, and theta is equal to PL square by 2 EI, you know that, but it is not acting at that location. So what we do, suppose there's a general thing, you know, up to node P, it is deflecting. Okay, but after P, it is straight line. Means this is a straight line. Means up to P, it is deflecting. After that, it is straight. Suppose if I draw like how it was original, this was original. So up to P, it is deflecting. After that, it is a straight line. So obtain, we need to obtain at B point D point at D point, what is delta? That is y. That is equal to, suppose this is L1. So P L1 cube by 3EI. And your theta is P L1 square by 2EI. I hope everyone it is directly up to B. You can obtain that. Now we have to obtain that C. So it is a straight line formula. Means what you can say that, so if this was your original position and it bends like this, and after that it is a straight line, so you obtained y up to here. Okay, now you need to obtain here. So use the equation of a straight line. What is the meaning of that? So you theta you obtained here. This is a slope that you obtained, and you know this. Sorry, you know this L minus L1. This is the distance. So use tan theta. So that tan theta is equal to this y dash by L minus L1. So because theta is so small, we can reduce tan theta to theta. So theta into L minus L1 is equal to y prime. Now you know y prime and you know here deflection. So total deflection will be delta at C is equal to y plus y prime. Now y is equal to P L1 cube by 3EI plus theta, that is P L1 square by 2EI into L minus L1. So if the load is not acting at that point, but you can always obtain what is the deflection at the end point. So I am asking, anyone have problem, please ask. uh, if you have clear the concept, please write clear, yes sir, I understand, I will move ahead. Hello, are you there? Please can you speak? You get what I want to say?
Sir,
Yes.
that tan theta is equal to y bar by L minus L1.
Yeah.
And the y bar means it will be tan theta into L minus L1. Sir?
Tan theta is equal to y bar upon L minus L1. You know this from this triangle because it is a straight line. Load is acting up to this. So up to load it is deforming. After that it is just a straight line. Okay. Then I assume tan theta is small. Then I assume tan theta is equal to theta, and then I equate theta into L minus L1 is equal to y prime.
Okay, sir.
Okay. Now I am going with a uniformly distributed load in cantilevers. Just write it and wait for a couple of minutes. Okay, now for uniformly distributed load in cantilevers. So it is given, this is a load beam and its load is given, uniform distributed load. EI are the properties normally. So first remember, this will always help you. You remember this. Okay, is equal to m. Now, if a load is you take x distance from here. Okay, what is the moment? So it will be m is equal to minus. Suppose this is a small w into x by 2, that is minus w x square by 2. I hope everyone know how to uh, obtain this. Can anyone have any problem? Then ask me, I will explain it to you. Do you know how to obtain this moment of for uniform distributed load? Okay, I assume that no one is commenting, so they know how to find it. Okay, now put it like ei d2y by dx2 is equal to minus w x square by 2. This is the rate of loading. Now, if I ei dy by dx, just write it, it will be minus w x cube by 6 plus c1. And again, if we integrate ei y, it will be minus w x to the power 4 divided by 24 plus c1x plus c2. Now the same equation at x is equal to 0, sorry, x is equal to L, dy by dx is equal to 0 and y is equal to 0. This implies we can obtain from this expression, and the equation we get is, that is I'm writing directly, it was, so ei into y is equal to minus sorry, w L cube x by 6 minus w x to the power 4 by 24 minus w L to the power 4 by 8. So you can see that the constant, your constant C1 is WL cube by 6 and your constant C2 is minus WL to the power 4 by 8. So constant C1 is WL cube by 6 and your constant C2 is minus WL to the power 4 by 8. Okay. Now what is the maximum deflection? So you know, in cantilever, maximum deflection is occurs at x is equal to 0. At x is equal to 0, ei y at 0 is equal to, what will be the equation? Minus w L to the power 4 by 8. So you can see that is negative, and this is the maximum deflection for cantilever with uniformly distributed load. And ei dy by dx is equal to w L square by 6 ei. So till now we studied two things: cantilever with uniform distributed and cantilever with point load. So cantilever with UDL is coming, that y max is equal to w L to the power 4 by 8 and dy means slope maximum is equal to w L square by 6 ei. So it might be w L cube. Okay, yeah, it is w L cube because it's a rate of loading. I hope this is okay with everyone for uniformly distributed. If any problem, please ask me. I'm giving you 1 minute. Please ask any question, then I will move ahead. Also, please write in chat box if any problem. So now I am going with a simply supported. Okay. So now I am going with simply supported. Simply supported beam with point load. So suppose this is a beam, this is given load W at the center, and this is your roller support, this is your fixed support, and your W load is acting, this is L. Now, this is R1, this is R2. So you know R1 is equal to R2 is equal to W by 2. Okay. Now, equation that equation that we all do, this is the equation is equal to M. Now, what is M? Suppose I take a M at this section. So M is equal to R1 into X. And now why I am taking it as like a positive, I'm going to show you. So because it creates the means we can say that it is creating the sagging part, so it is positive. So in this case you should know that if it is creating the hogging part, so it will be negative, and it is if it is creating sagging part, it should be positive. So if I put that R1x here, it will be pi d2y by dx2 is equal to R1x. So if I integrate it once, we get pi dy by dx is equal to R1 x square by 2 plus C1. Now if I integrate it again, it will be pi y is equal to R1 x square by x cube by 6 plus C1x plus C2. Now what are the boundary condition in this problem? You can obtain that at x is equal to 0, y is equal to 0, because here, because of the support, there is no any deflection. But you cannot say that at this point the slope is 0. Why? Suppose if I draw the like the by deflection like this, no, now it has an angle theta. You can see that this is the angle theta. So you cannot say, but at the middle you can see the deflection, the slope is 0. It is 0 because it is horizontal. If you say this is x, this is y, so it is parallel to the x-axis, so it is 0. So at x is equal to L by 2, theta is equal to 0. This is a boundary condition, and it is changed in this case. So in simply supported, these are the boundary condition, and in cantilever, the other two one the boundary condition. And if you solve that, y we got is W x cube by 12 minus W L square x by 16. Okay. Now, what is the maximum deflection? Maximum deflection is occurring at x is equal to L by 2. You can see that this is the maximum deflection y. So y maximum is equal to, put x is equal to x by 2 to get W L cube by 48 L. Okay, and theta maximum is equal to, you can get theta maximum is uh, W L square by 16 L. So these are the two values for cantilever, for simply supported with point load. Okay. Now I'm going with simply supported with UDL now. So now simply supported with UDL, with UDL. And if we just see that the const for knowing the constants, the boundary conditions are same at x equal to 0, y equal to 0, and x equal to L by 2, theta is equal to 0. And this is R1, this is R2, this is W per meter. Okay. Now what is the moment M? M is equal to R1x minus W into x by 2. That is equal to R1x minus Wx square by 2. Now R1 is WL by 2 into x minus Wx square by 2. So this is your moment. Now you put it in the equation, EI d2y by dx square is equal to WLX minus WS square by 2. Just integrate it like that and you get the 2 y max y equation is a function of x and theta is a function of x. And your maximum value will be 5 WL की power 4 by 384 EI and theta maximum is equal to means 20, I think 24. Theta maximum is yes 24 WL cube by 24 EI. So you need to learn this. Means literally learn this. In exam, there is no time just to you cannot derive all these things. So I am going to make a table. So uh, so for cantilever at point load, this is your equations. Now cantilever same at UDL, you get y maximum and theta maximum, and that is equal to you can say here I derived it. So let me see. WL to power 4 by 8 and WL cube by 6 EI. Okay, so let me write it here. It will be WL to power 4 by 8 EI and WL over WL cube by 6 EI. Now, for you simply supported, what is the value? For simply supported, we can get y at point load. At point load. At point load, y maximum is equal to WL cube by 48 EI and theta maximum is equal to WL square by 16 EI. And for UDL, it is y maximum is equal to 5 WL4 by 384 EI and theta maximum is equal to WL cube upon, I think it is 24 EI. So what are the locations? These the maximum is at free end, free free end. This is also free end, and this is also free end. And in this equation, this is at center, and this is also at center, and these two are maximum at ends, at supports. So now you there are very much things I need cleared in this point. So if anyone has doubt, just ask me, because now I am going to give you some question. Just I want you to please ask quickly because I need to cover 3 more topics in 5 minutes. Any problem in this? Please, can anyone ask? Hello, are you there? Anyone there? Hello.
Sir, just a confirmation, sir.
Yeah.
Both y maxes of simply supported are acting at the center, sir.
No, this is most simply supported, but this is for point load and this is for UDL.
Yes, sir. But both y max at the center and theta max at the support, sir.
Yeah, both are the same.
Yes.
Because if you just go it with just I'm just going there. So if you see that this deflection, this will be like this only, the above. But here we can see that the slope is 0 at the center and maximum slope is occurring at the ends. Now you are visualizing what I want to say.
Yes, sir. Yes.
And now this is a maximum deflection. So in this, the maximum deflection is occurring at center and maximum slope at the ends. And for this also the same case. So now I am doing with Macaulay's method. So in it there are a few rules. First write the rules. Write the rules. That is first, uh, always take origin on the extreme left. Extreme left. Second thing is take left clockwise movement as positive. Okay, sorry, this is not positive. This is negative. And anti-clockwise as positive. As positive. Okay, now I'm going with us just same problem. So if any uneven loads are given, then you can easily obtain because in other case, double integration method, for every particular case, you need to obtain the two constants. So in it, you can go with a single constant only. So suppose uh, this is your simply supported beam. Okay, now W load is acting. This is L by 2. This is L by 2. Now take we have to write moment as just above the rules. So if I take moment at the extreme left, this is the origin. Take any distance x. So this is W by 2 at a at a, and this is also W by 2. Now what is take any distance x? Suppose I take here also x. So it will be W by 2 into x, but it is in the clockwise direction, so it will be negative. Okay, plus there is a term. This is a, you can say, a bracket, but that is in this form, and it will be W into x minus L by 2. So if you take both loads simultaneously, so it will be like this. So let me say where here. Now if I take x here, okay, then the W will act like L by 2 minus, sorry, this x here, then it will be as whole x and minus L by 2. Now why I'm writing this, I'm going to tell in just a couple of minutes. And this part will act only when x is greater than L by 2. If x is less than L by 2, you will not consider this as your means function. You will take only this. When x is greater than L by 2, you will consider this. Then both functions will operate simultaneously. But if x is less than L by 2, you will only consider this function. Okay, that's why I am writing it in the brackets. It will operate only with this condition. Now, just put it in the formula. EI d2y by dx square is equal to minus w by 2 into x plus this bracket w into x minus L by 2. And now integrate it with respect to x. EI dy by dx, that is equal to minus w by 2 into x square, this is 4, plus take it like this, w. Now integrate whole, that is this will be whole, means this will not be indivisible term. This will integrate by whole. Okay, So you can say this is x minus L by 2 whole square. Now plus C1. And now again, EI y is equal to minus W. If we just give it, it will 12 x cube plus W x minus L by 2 whole cube by 6 plus C1x plus C2. This is your equation. Now I know that it is if you haven't studied it earlier, it would be difficult for you to grasp. So I am just going with it, and one or few problems you will understand how it is calculating. Okay. Now we have to obtain C1 and C2. Suppose you know that at x is equal to 0, your y is equal to 0. Now x is equal to 0, that means it is less than L by 2. Now we need not to operate this term. Okay. So EI into 0 is equal to minus W 0 cube by 12. We will not operate this term, second term. We will leave this. And then C1 into 0 plus C2. That means C2 is equal to 0 from this equation. Now, what is C1? Now, again, what for C1, we will take at x is equal to L by 2 y prime, that is theta, or that is dy by dx, is equal to 0. Now at x equal to L by 2. So if we operate, just take it also, it will be 0. So we will not operate it. It should be at greater than only. So 0 is equal to L by 2. We will put W L square by 16 plus C1. So your C1 will be W L square by 16. Now put it in the equation of y. Y is equal to minus W x cube by 12 plus W x minus L by 2 whole cube by 6 plus W L square by 16 into x plus C2 is equal to 0. Okay. Now you know that the maximum is occurs at x is equal to L by 2. Okay. Y max. So put x is equal to L by 2. You will get same expression. This implies y is equal to minus W L cube by means if we just write it L by 2 whole cube, it will be it is 12 inches of this plus W L square by 16 into L by 2. And if we solve it, it will be W L cube by 48 EI. That we use just we obtained earlier in the case. I hope you remember that in this case also, in this case also, we obtained the same expression, and here also we obtained the same expression. Now just okay, you can say double integration we are doing here also and there also, but let me give you another. Suppose the load is not acting at the center and it is acting slightly left or right, then going with double integration will be very means tedious one. So you need to go with this method only. So suppose I'm just giving you a question. uh, not with that, let me give you this question. Suppose this is a B, this is A, this is B, and you have 12 Newton at this point, 12 kilonewton, and 8 kilonewton at this point. You have length is 6.5 this much. This is point C, this is point D, this is 3 meter, and this is all this is 4.5 meter. Now you need to obtain the deflection at y at C and D. You need to obtain deflection at y, C and D given E is equal to 200 gigapascal and I is equal to 160 into 10 raised to power 6 mm to power 4 mm. So Go with the integration method, double integration. You will find it very, very lengthy because you have two loads. You cannot simply put one. So then this method that is called the Macaulay's method is very useful. In single expression, you can find this. Now I am telling you how. So first of all, obtain the reaction. RA is equal to, I am writing that directly, 8 kilonewton and RB is equal to, sorry, this is this way. Okay, this is 6.5, this is D. So RA is equal to 12 kilonewton and RB is equal to 8 kilonewton. Now we can now write as it suggests. Moment is equal to, it is clockwise moment, so it will be negative minus 12 into 10 raised to the power 3 into x. Okay, then plus this will in a separate form. Then what will be the other equation? The other equation will be 12 into 10 raised to the power 3 x minus 3. Means this is 3, so x minus 3. Now another equation, that is 8 into 10 raised to the power 3 x minus 9.5. Up to here, it is clear that what I write. Please tell it is clear. Hello. Can anyone speak or everyone is sleeping? Hello. Please. Hello. Anyone is there? Okay. Uh, you got this expression? How I am coming with it?
Yes, sir.
Okay. Now, suppose if I integrate this, then if we go with simple double integration method, you know that in double integration method, for every part, you have to integrate it again and again. So let me go with it, integrating that Ei d2y by dx2 is equal to m, that is equal to minus 12 into 10 raised to the power 3x plus 12 into 10 raised to the power 3 x minus 3. So I was here. So am I audible? Is it now okay?
Yes.
Okay. Now, so just got disconnected. So plus 8 into 10 raised to the power 3 x minus 9.5. So you can go with separate terms. This will operate at A and C, and 12 Newton, and this portion will not operate here. Now after this 3 meter, this both will operate and this will not operate up to 6.5 meter. And after 6.5 meter, these three terms, all three will operate. Okay, these are like the selective conditions you put. Now EI dy by dx, if we just integrate it, it will be minus 12 into 10 raised to the power 3 x square by 2 plus 12 into 10 raised to the power 3 x minus 3 whole square by 2 plus 8 into 10 raised to the power 3 x minus 9.5 whole square by 2. Okay, now just integrate it once. Sorry, plus c1. Ei y is equal to minus 12 into 10 raised to the power 3 x cubed by 6 plus 12 into 10 raised to the power 3 x minus 3 whole square by 6 plus 8 into 10 raised to the power 3 x minus 9.5 whole cube by 6 plus c1 x plus c2. Now, what is the boundary condition for that? First, the boundary condition is we cannot say anything about deflection, where deflection is maximum. So, can anyone say what are the boundary conditions now? Deflection can be maximum at any place. Theta is equal to 0. You also cannot say where theta is equal to 0. So, what will be the boundary condition? You need two boundary conditions to find two constants. Can anyone help me to find out? Hello. Can anyone find out what are the two boundary conditions? Hello. Can anyone tell me what are the boundary conditions? Okay, let me write. You are not saying anything. So we cannot anything about where theta is equal to 0 because it is not symmetrical load. At symmetrical load you can say, at cantilever you can say, but here you cannot say. So you need to put these two equations at x is equal to 0, y is equal to 0, and at x is equal to L, y is equal to L. Okay, these are the two boundary conditions. Means here also the deflection is 0, here also the deflection is 0. Put these two boundary conditions and your final equation will be, just I'm writing, your C1 and C2 will be, what is the value of C1 and C2? C1 is equal to 193.2 into 10 raised to the power 6. Okay, and your C2 is equal to 0. So EI y is equal to minus 12 into 10 raised to the power 3 x cubed by 6 plus y same expression, that same expression here, same expression here, plus 193.2 in 10 to the power 6 x. Okay, now we have to obtain that c. Put x is equal to whatever the location at c, what is the distance? 3. At put x is equal to 3, we can obtain yc, and put x is equal to 6.5, you can obtain yt. Okay, these are the two points you need to find. Now this is easy. I know, matlab, this is not very easy. You can go with it, but this is the Macaulay's method, and this will help you to find the things that is not symmetrical. You can go same with the okay. Let me go with a problem that is not of Macaulay's method, but from the double integration in cantilever. Okay, so I will go and come here again. So suppose this is given this is a cantilever. Okay, now it is given that it is a UDL, but UDL is only up to half. Okay, this is W per meter, and suppose this is whole length is this is L by 2 up to here, and this is L by 2, and you need to find deflection at point. Suppose this is point B, C, and A. We need to find deflection Y at B. Okay, now how will you obtain Y at B? It is given half load. Okay, so in that condition, we can take simply if you doesn't want to do double integration method, Macaulay's method. So what I will suggest is, okay, Let us make a little slight adjustment. Suppose if I just draw complete UDL. Hello, you draw completed UDL. This is a point C, this is point B, this is point A, this is L by 2, this is L by 2. Now, but why I add extra node? Then I need to subtract that extra node. So I from the back side I am putting extra node in upward direction. So this will nullify each other, and this can be simply distributed to these 2 points. A UDL up to full length plus a UDL from bottom. Now you can apply the principle of superposition, because in this part this part how to solve this. You also know how to solve this, but you don't know how to solve this. So we can easily reduce to that part. So here the y is equal to, at this point, is W L4 upon, what is the formula? Let me see. ATI, okay, upon ATI. Now, what is the here? What is it tends to bend downward and it will tend to bend it upward. So it will be negative. Then we had to obtain here. So we will obtain here, and we will use the equation of a line that we used earlier. So it will be W L by 2 whole power 4 upon ATI. This one the deflection plus the slope. If it will deflect like this, so this is the slope theta, this is the deflection we need to find, and this is L by 2. So your W into L by 2 into Q by 6 EI into L by 2. So this will be your answer for Y at the extreme point. So this is for the cantilever. So from Macaulay method and deflection double integration method, anyone has any problem? Yeah, at least someone respond, because at this I'm going to ask, then I will not able to complete the syllabus. So now I'm going with the moment area method. So if a body, suppose, just like in double integration is useful for single load, or is not, even you can say it is not very useful, not very useful, because you need to operate every time at any load. If any load is acting, then separate equations. This method, Macaulay's method, is useful for any type of loading, any type of loading. But if something is given like your beam is not of same material, they are made up of different materials. Suppose this beam is cross section area is changing, or this beam of one material of aluminum, another material of steel. Now this will not help, because you know that we are putting EI outside the integration. That means they are the constant term over the length. We cannot use this formula. We cannot use this formula here. So what we will do? We will use moment area method. And moment area method can be used in other cases also, but this is the most common example for moment area method. So in moment area method, we have two theorems. That is theorem 1, that is a slope. The slope, for slope, you need to find the area between the points, and divide it by EI. And for theorem 2, deflection, delta or deflection, we have find the area between points, multiply it by x bar, that is the center of what is the center of gravity of that area or center of that area by EI. Okay. So these are the two theorems and means what their meaning I will explain here. Suppose uh, if a if I say okay, just take you just take simply separate wing. You apply load 1 here, load 2 here, and this is reaction 1 RA, this is RB, this is L, this is L by 2, this is L by 2. Now, what how to solve that with moment area method? So, moment area method. So, first of all, draw the bending moment diagram. This is your bending moment diagram. Okay, and its center value is WL by 4. This is x is equal to L by 2. So I'm just coming in 1 minute. Please do write this. Okay. So in moment area method, uh, what we will do is suppose you know that at center in UDL at center, sorry, in simply supported at center deflection is 0. We only need to in moment area method we can be applied when we know any reference point. Otherwise, differences will be obtained. Now, how I am showing you? Suppose this is the 3 points A, C, B. Now, if you want to find the deflection at delta A, with the deflection at sorry slope at A. Now, slope at A minus slope at some point where this can be turned out to be 0. This is equal to area between A and C divided by EI. Okay. Now, what is the sort of slope at C? 0. Okay. Then theta A, that is a slope. Area between A and C is this is triangle here. This is equal to WL by 4 into L by 2 into 1 by EI. That will equal to, and it's also half into base into height. WL by 16 EI. Okay. Now This is a moment area method, and you can see it how easily we can find the slope. Now, if everyone is with me, you can see that how the easiest way to solve any problem is moment area method, but you know to find that area. Suppose this is triangle. Now, if it is parabolic, what will you do? How do you find the area? Then again, it will radius. So, easy curves can be easily obtained. Now, what for deflection, we need to find delta A minus delta C. Suppose we write it inverse. So delta C minus delta I, because at A it is 0. So take any reference where the value is 0 and area between them into x bar divided by EI. Now what is the area? We already obtained WL by 16 EI. Now from the end state where you need to obtain, this is your point now. Take the centroid, means here from here, sorry, not from here. Oh, take just a second. Uh, here this is a reference point. Now take the centroid of the area from this. Means this is a triangle, so it should be 2L by 3. 2, 2 into L by 2 by 3. So it will be L by 3. So take the center of the area and multiply with it. So it will be L by 3. So WL square by 48 EI. So you can see without doing a double integration, without doing anything, you can simply obtain the area. Now, just I'm going with another problem. This is the moment area. Suppose this is given. Uh, goodness. Suppose this is a beam, and you cannot, because of the irregular processing, you cannot solve it by this. And you have one moment M here acting, one moment M here acting. Okay. Now here also you have 2M. Because of the anti-couple, it is just to make it in that, sorry, not in this direction. It will be in this direction to balance the moment. Now here it is 2EI, here it is EI, and you need to find the deflection and the source. Suppose this is cantilever. You need to obtain the deflection and the slope at this point. Now what we need to consider is, suppose if I draw the bending moment diagram, okay, then you can see that the bending moment diagram is equal. So this is M, this will add up M, so it will not like that. This is M up to here, then it will add up M, and up to here it will be 2M. Okay, this is M, this is 2M. Now if you divide it by EI, then if you divide by EI, it will be by 2EI, and here it will be, suppose this is a portion. So if you divide this by M by EI, so it will be like this. It will be 2M. So it will be 2M by 2EI. You cancel 2, 2. That means your M by EI diagram will be like this. Means equal. Or you can simply say this is the, or I can simply write. I am not going to do that about this. So suppose this is C, this is B, this is A. You obtain theta, you want to obtain theta C. So theta C minus theta A is equal to area divided by EI. What is the area? So this area is M by, so M in by EI into L by 2 plus this area is 2M divided by 2I into L by 2, because this is rectangle. So L by 2, this is L by 2, and this is height divided by E. What is the value? So if we cut this M by EI into M by EI into L. So this is your theta C minus theta I. that is equal to m by pi into L. And you know theta a is equal to 0 because at a in the cantilever slope is 0. So theta c is equal to m by ei into L. How many of you got this? Just message me if you are with me, or I have to do it again. I'm waiting. Please say something. If any problem, then also I will explain. Okay. Now, I will. What is the deflection at point C? Suppose this is A, this is C. Then what is the deflection? Then take deflection C minus A. That is equal to what is the area? We just obtained the area. Here, this is the area. Okay. So M by EI into L. This is the area, and we have to multiply it with X bar. So what is the X bar? So this is L by 2, this is L. So pole is L, so center is L by 2 multiplied with L by 2. So it will be M L square by 2 EI. Okay, this will be your deflection at point C. So I'm going with some another question. Now suppose I am going with cantilever now. Cantilever means point low. Suppose I am given cantilever. This is your cantilever with P acting, and this is L. Okay. Now, what is the bending moment diagram for this? Just you can easily say this is a hawk, so it will be negative y-axis. So it will be like this. So it will be negative in negative y-axis. Okay. And your maximum bending moment, that is PL. Here PL. Now you need to obtain. Suppose this is A, this is B. You need to obtain theta B. So take reference, what is 0? Theta A is 0. So theta A is 0. So like it, write it like this. And area between that is 1 by 2 into dl into L. So it will be, so by EI, PL square by 2 EI. Okay. Now you got theta B minus theta I. And you know theta A is equal to 0 in cantilever. So theta B is equal to PL square by 2 EI. Now if I want to find the deflection at B, deflection B minus deflection A is equal to PL square by 2 EI. This we already obtained. And what is the what is the value of the value of the that support this center of gravity from the end means from where we want to find out this end. So it will be 12 by 3. So if you put that 12 by 3, it will be PL cube by 3 EI. Okay, so this is 0. So delta V is equal to PL cube by 3 EI. So this X bar should be from the end where we need to calculate. Means if you want to calculate at this point, then the center of area will be calculated from this only. This is the main thing. Now after this, uh, we are going to do with the propped beams. Propped beams means suppose what are the propped beams? They are like, suppose you have a cantilever, and as you know cantilever deflect very much. So they provide a support reaction at the end not to deflect very much. So these are called the propped beams. Propped means they are a load is that is called the prop. This is called the prop. This is probe is acting so that the deflection is not very much. So earlier when it was not there, the deflection would be like this. But as you know, it was there. So now the deflection is like this. Okay. Now the deflection is not very much and a reaction force is acting. So that's why it is just provided so that the deflection for the cantilevers and for the from wherever the required would not be much. So this is the application of problem. Now we are going to use with some questions so that you can understand how the concept of problems can be used. Suppose you have uniformly distributed load on a cantilever beam of length L and omega is weight per unit length. Okay, then they ask, suppose a prompt reaction force is a support is acting in this way. So this is P. Now we need to obtain what are the force P. What are the force P to stop to stop, no, we cannot say this, to make deflection 0 at B. Now deflection at B from the, if it's just simply distributed from the superpositions theorem. So if deflection is this much plus, suppose a load is acting in this way B. Now will be the deflection at B from this load? You can know from the general expression that W L power 4 by, I think it is 8 or 6 I need to see. Yeah, it is 8 So for this, and now when the P support is acting, what is the deflection? Deflection delta PL cube by 3 Now, since delta should be equal, means at B, and because of this UDL, and at B because of the P should be equal to 0, that means, yeah, that means the delta 1 plus delta 2 should be equal to 0. Now this implies WL power 4 upon ATI should be equal to PL by 3 because they are in opposite direction. So you can add negative here and then take it other side to positive. Now, what is the value? You can obtain P as 3 by 8 WL. So this is the reaction force that is occurring at the top section. Okay, this is the one type of question. In other type, I am going to say you. Suppose you have a beam, and to avoid its very much deflection, you have another beam like this. Okay, at here, and you have a roller support at here. Means it is a roller supported here. So okay, now like this. So you can say this is A, this is B, this is C, and this is D. And it is given that this omega W is 15 kilonewton per meter. This is 2 meter, and this is 1 meter. So you need to obtain the reaction force at C. Reaction force at C. So from the just like we earlier did. So let us suppose that this from the two parts we can make it like this. So if we divide it, so a load is acting in this way, and suppose this will provide a support reaction in this direction, and here also this reaction is coming in downward. Now reaction force at C, so that means that deflection at this point should be equal, means the how much is deflected should be equal to this deflection. That means what is the value of deflection from this UDL? WL for 4 upon 8 EI. And from this P, this is the reaction force that is coming. What is deflection in that? That is PL cube by 3 EI. Now equate these two terms. Here L1 and L2 are different. Equate these two terms. WL1 for 4 upon 8 EI is equal to PL2 cube upon 3 EI. Now you can get simply the reaction force from this is no there is slight change. Let me do that. A should be not equal. So no. One thing one thing I have done wrong. Let me correct it. Uh, so what is wrong? Let me tell you. So so what is wrong? Let me tell you. So you can see that here a P load is acting here. Huh? So you cannot write like W. You cannot write it like. Okay. Now I cannot write it like this. Now what will the change? WL power 4 upon 8 Ti minus, because of the P load in the upward direction, it will be minus PLQ by 3 EI. This should be L1. And this is equal to, now here that P load is coming, so PL2Q by 3 EI. Now this is equal, so you can directly obtain the P. WL power 4 upon 8 EI is equal to P upon 3 EI L2Q plus L1Q. From that, the reaction force is coming, that is P is equal to 10 kilonewton. Okay, so this is the question that from the proud means. So can anyone unmute and explain how this is happening, and is it they got it understand or not, please? Please, anyone is there? Please just speak. Hello. Am I audible? Okay. So up to this point, it is there. Let me. So let me give you another question in the cloud beams only. So problems is a very interesting topic. Direct formula-based questions are coming, and you can easily solve that. Suppose this is point A. A spring is acting in between two beams, and here another beam. That is, and now it is B, it is C, it is D. Now you need to obtain, find the extension in that. Means what is that extension in the spring? So, or I should take another example because it will go very big. So, so I am just not going with this question because it will go very big. let me simply write the equations that is needed for deflection of beams. So in deflection of beams, you can write, or if you want, in deflection of beams for UDL, for cantilever, you have generally three types of load. The first load is point load, the second is uniformly distributed load, and the third one is uniformly varying load. Varying load means this is a load. Suppose you have a beam like this, and your load is varying like this. It is uniformly varying like a triangle, or like this. You can say anything. So for a triangle, I am saying this for a triangle. So consider for triangle only. So or write it only for two things: point load and UDL. Don't consider it. So for point load, it is PL cube by 3EI, and it is PL is, sorry, this is for deflection, and for slope it is PL square by 2EI. Here it is Y is equal to PL. Here the Y value is Y is equal to WL 4 upon 8EI, and your deflection is, sorry, theta is WL cube upon 6EI. So you need to remember these things for cantilever. Now for simply supported, Y maximum is equal to W L cube upon 48 EI, and theta is equal to W L square upon 16 EI. So your Y is equal to, for UDL, 5 WL for 4 upon 384 EI, and your theta is equal to WL cube upon 24 EI. Okay, so these things you need to remember and learn, and then your moment area method, it is, first theorem is slope. So theta b minus theta a is equal to area of moment from A to B by EI, that is area only, area of bending moment upon EI, and your theorem says minus A is equal to area of bending moment divided by EI into x bar, and this x bar from the B point, means this x bar should be center of area from B point, from point B. So today we learn about the bending stresses, shear stresses, and the deflection of beams. So I hope you everyone has a great previous year. So please, I would suggest, please go with it. Uh, for previous year, solve the questions. If you don't have any problem, just mail me. I have just mail ID given to you. Okay, and the YouTube link I shared, I will upload the lecture so that you can